Stack overflow, segmentation fault, out of memory, killed. 4 different errors, 4 different cryptic messages. And if you're like most developers, they all mean the same thing. Something broke, somewhere, for some reason. Here's the secret. They're all the same story. Your program gets exactly 2 places to keep things, and each of those errors is one of the 2 places, breaking its own rules. Learn the 2 neighborhoods, and crashes stop being random. Let's draw the map. When your program starts, it gets one long strip of memory. At the top, the stack. It grows downward. At the bottom, the heap. It grows upward. 2 neighborhoods moving toward each other with completely opposite rules. Keep this picture. Every crash in this video happens somewhere on it. The stack is where function calls live. Every time you call a function, the program stacks a tray on top. That tray, a stack frame, holds the function's local variables, its arguments, and a note saying where to return to. Call another function inside it? Another tray goes on top. Return? The top tray comes off and everything on it is gone. Instantly. No searching, no bookkeeping. Just push and pop. That's why the stack is fast. Allocating is literally moving one pointer. But it has 2 hard limits. The trays are rigid. Their size is fixed at compile time. And the whole tower is small, a few megabytes. That's it. One consequence trips everyone. A local variable lives on its tray. When the function returns, the tray is destroyed, and the variable with it. So if you keep an address pointing into a dead frame, you're pointing at reclaimed ground. The next function call builds a new tray right on top of it. Your data is gone. The stack forgets. That's the deal. It's what makes it fast. Now, break the stack's rule. Write a recursive function with no exit. It calls itself. New tray. Calls itself again. New tray. Faster and faster, the tower grows down until it slams into the boundary. There's no room for one more frame. The program dies. That's a stack overflow. It isn't mysterious. It's a tower of trays hitting the ceiling. And it's almost always the same bug. Recursion that never stops, or data too big for a tray. Everything the stack can't handle goes to the other neighborhood. The heap is big, gigabytes, not megabytes. And it's flexible. You can ask for any amount of space at any time, and it lives as long as you want. But nothing is automatic. You ask, give me 64 bytes. An allocator searches the warehouse for a free slot, marks it taken, and hands you back one thing: the address. That address, the pointer, is your only claim to that memory. And the warehouse has one iron rule. When you're done, someone must give the slot back. In C, that's you, calling free. In Python or JavaScript, a garbage collector does it, by watching until nobody points at the slot anymore. Slower than the stack, much more powerful. And every remaining crash lives here. Break the warehouse rule one way. Give the slot back, then keep using it. You free the memory, but you still hold the address. The allocator hands that slot to someone else. Your old pointer now points into somebody else's data. Write through it, and you corrupt a stranger. Read through it, and you get garbage. Step outside the map entirely, and the operating system stops you cold. Segmentation fault. A seg fault is not the machine being moody. It's your program touching memory it doesn't own, usually through a pointer that outlived its slot. Now break the rule the other way. Never give the slot back. Allocate. Lose the pointer. That slot can never be freed. Nobody remembers where it is. Do that in a loop, and taken slots pile up, request after request, hour after hour. The program doesn't crash today, it just gets fatter. That's a memory leak. And garbage-collected languages are not immune. Keep a reference alive in some forgotten cache or global list, and the collector must keep the memory alive too. Leaks in Java and JavaScript are real. They're just leaks of references. Leak long enough, or genuinely need more than the machine has, and the warehouse fills. An allocation comes back empty-handed. On a server, the operating system may pick your process and kill it. That terse "killed" in your logs is often exactly this. Out of memory is the heap's final answer. There is no more warehouse. So, what goes where? You mostly don't choose. The rules do. Small, fixed size, short-lived, locals, arguments, return addresses, stack, automatic. Big, growable, or outliving the function that made it, objects, buffers, anything behind a pointer, heap. Same story in high-level languages. Python and JavaScript put almost every object on the heap and keep the stack for the calls themselves. The two neighborhoods are still there. The garbage collector just walks the warehouse for you. 3 things to keep. 1. The stack is automatic and fast because it forgets everything on return. Stack overflow means the call tower hit its ceiling. Look at your recursion. 2. The heap is powerful because it forgets nothing until someone gives the memory back. Segfaults and leaks are the 2 ways that handoff fails. 3. When a crash names memory, ask one question first. Which neighborhood? The error message almost always tells you. Next crash you see, you'll read it differently. A tower that hit its ceiling. A pointer that outlived its slot. A warehouse that filled up. If this made memory finally click, share it with someone who's staring at a segfault right now. And subscribe. More of what's under your code opened up.